Hello again. This is section 3.5, complex zeros and the fundamental theorem of algebra. So what we're going to do now is expand on that idea of complex numbers that we looked at in section 1.6 and look at how we can actually find zeros of a polynomial that happen to be complex numbers. And then we're going to use that then to actually define what the fundamental theorem of algebra is in terms of our polynomials now. Okay, so our fundamental theorem of algebra, every polynomial, right, and this is that same form of a polynomial that we've looked at before, with complex coefficients, right? And we've already said that all real numbers are technically within the complex numbers also, because any real number can be written in the form a plus bi, where the b value just happens to be 0, okay? So as long as you have complex coefficients, it has at least one complex 0. So in this case, right, we're going to look at the fact that every single polynomial is going to have at least one complex 0. Keep in mind, though, that that complex 0 could be a real number, right? It doesn't have to be imaginary. It could be real, but it could also be imaginary, right? And so now we have those imaginary numbers to work with in terms of finding the zeros of these polynomials. All right, now our complete factorization theorem. If p of x is a polynomial of degree n greater than or equal to 1, then there exist complex numbers a, c1, c2, and so on, right? So these are all constant values that are complex numbers. A can't be equal to 0, such that we can actually factor this polynomial into each of these factors with that leading coefficient of a out front now as that first factor. Okay, so just keep in mind the C1, C2, and so on. Those are all complex numbers. Could be real, could be imaginary. We don't know. Okay, but we'll be able to factor it all the way down into this list of factors based off the zeros of that polynomial now. All right, so we're going to let p of x equal x cubed minus 3x squared plus x minus 3. We want to find all the zeros of this polynomial this time. Okay, now we're going to start this the same way we started the problems back in section 3.4. We're going to use our rational zeros theorem. We're going to find our p's and q's. We're going to look for those zeros that work using synthetic division. And then we're going to use either quadratic formula or factoring to find any remaining zeros that we might not get from the rational zeros. Okay, so we're going to start with p's and q's. I'll list my p's. Remember, we're looking at the 3 in this case. Factors of 3 are just 1 and 3. So we have a plus or minus 1, plus or minus 3. Now we're going to look for our q values. That just comes from our leading coefficient, which is an understood 1 this time. So that's just going to give us plus or minus 1 for those factors. Then we divide p over q. Well, in this case, that's just 1 divided by 1, which gives us 1, and 3 divided by 1, which gives us 3. So we have plus or minus 1, plus or minus 3. Now, remember back in section 3.4, I said at that point we can look at our graph to determine which of these zeros might actually work. Okay, so in this case, the first one I'm going to test is going to be the 3. Again, I got that just by looking at my graph to see where it looks like it might cross the x-axis. So now when we test this, we're going to actually use our coefficients here. We have 1, negative 3, positive 1, negative 3. We bring down the 1. 1 times 3 is 3. That gives us a 0. 0 times 3 is going to be 0. 1 plus 0 is 1. 1 times 3 is 3. And negative 3 plus 3 is 0. Remember, that 0 is the remainder now. Now, since we started with an x cubed and we found a 0 that actually works, that tells us then that x minus 3 is one of our factors, and what's left over now is going to be x squared plus 1. Because again, remember, if we start with an x cubed, we factor out one of our x's, that means that what's left on that line at the bottom there is going to represent an x squared. So we have 1x squared plus 0 x's, and then the 1 is our constant, with a 0 as a remainder. Now, that only gives us one of our zeros, because in this case we have a 0 of 3. To find the other zeros now, we have to look at the rest, what's left over, which is the x squared plus 1. Now this time, because it's a simple quadratic, right, there is no b term, I can actually just set this equal to 0 to find the rest. So I'm going to say x squared plus 1 equals 0. You could also use quadratic formula if you want to. Just understand this is not going to factor because it's not a difference of squares, right? So we have to either solve it this way or using quadratic formula. I'm going to subtract my 1. That's going to give us x squared equals -1. Take the square root now. That's going to give us x equals plus or minus the square root of -1. This is where section 1.6 comes in. Now we have a negative under our square root, so we know we're going to get an imaginary number. The square root of -1 is just equal to I, so we're left with x equals plus or minus I. So now in terms of our zeros, that means we have a 0 at I, and we have a 0 at -I. That gives us all 3 of our zeros for that polynomial. Now, for the complete factorization, we know again that x minus 3 is one of our factors. And now we can actually use these complex numbers as our other factors. Well, if I is a 0, that means that x minus I must be a factor. And if -I is a 0, then x plus I must also be a factor. So that would be our complete factorization now using complex numbers, right? That can include imaginaries. That's our complete factorization for that polynomial. But again, we start out the same way, find your rational zeros, use your synthetic division, right, to get one of those out of there, one of those factors. See, once you get down to a quadratic, then we can either use quadratic formula, or in this case, just set it equal to 0 and solve. That should give you any complex zeros that you might also have here. All right, so same thing, we've got x cubed minus 2x plus 4, find all the zeros. So again, I'm going to start here with p's and q's. I'm looking at the 4 first for my p-values. So that's going to be plus or minus 1, plus or minus 2, and plus or minus 4. Q values, again, leading coefficient here is 1, so that's just going to be plus or minus 1. When I divide p over q now, I'm just dividing each one of those p-values by 1, so we get plus or minus 1, plus or minus 2, and plus or minus 4. All right, now we do our synthetic division. In this case, right, if you look at your graph, it looks like -2 is one of the places where we cross the x-axis. Okay, so I'm going to use -2 here. I'm going to list out my coefficients. We have 1. We're missing the x squared, so we have to put a 0 in its place. -2, and then 4. Bring down your 1. 1 times -2 is -2. Now we add 0 plus -2 is -2. -2 times -2 is +4. -2 plus 4 is +2. 2 times -2 is -4, and that gives us a remainder of 0. So now in terms of my factors, what I've got is x plus 2 has to be a factor because of the -2 being 0. And now, because we started with x cubed, this line is x squared minus 2x plus 2. All right, now this time we can't just set it equal to 0 like we did last time. We can't factor it either, okay, because the only factors of 2 are 2 and 1. That's never going to give us a -2x in the middle. So for this one, we are going to have to use quadratic formula to find those other 2 zeros. I'm going to come down here, x equals -b is going to give us +2 plus or minus the square root of -2 squared minus 4 times 1 times 2 all over 2 times 1. And now we just need to simplify that. So we have 2 plus or minus the square root of 4 minus 8 all over 2. Well, 4 minus 8 is -4, so we have 2 plus or minus the square root of -4 over 2. Now we can take the square root of -4. Remember, the square root of a negative gives us an I. The square root of 4 is 2, so we're going to have 2 plus or minus 2i all over 2. And now everything is divisible by 2 here, so I'm going to divide each term by 2. 2 divided by 2 gives us 1, plus or minus 2i divided by 2 is just 1i. So now in terms of our zeros, We know that negative 2 worked, and now we have 1 plus I and 1 minus I. So that gives us our list of zeros for this polynomial now. Now for the complete factorization. Again, we know that x plus 2 is a factor because negative 2 is one of our zeros. Now, to get the other factors, we're just going to do x minus each of the zeros. Okay, so in this case, that's x minus 1 plus I and x minus 1 minus I. And so even though these are complex numbers, now they have an a and a b part, we can just do x minus whatever that complex number is, and that will give us the corresponding factor for that zero. At that point, we can go ahead and just distribute the negative to drop that extra set of parentheses inside. This is going to give us x plus 2 times x minus 1 minus I, and then x minus 1 plus I. So this right here would be our complete factorization for that polynomial. Just keep in mind, whenever it asks for complete factorization, we're looking for the linear factors with just an x to the first power that have complex numbers now as those factors. Okay, so we can use the 1 minus I and the 1 plus I as the zeros to get those factors now. Everything should be an x to the first power as our factors. All right, now our zeros theorem. Every polynomial of degree n greater than or equal to 1 has exactly n zeros. So basically, if we can look at the degree of the polynomial, that will tell us exactly how many zeros we will have, provided that the zero, that a zero of multiplicity k is counted that many times. Okay, so let's say you have like an x minus 2 squared. We know that has a multiplicity of 2 because of the square. We have to make sure we count that zero that comes from that factor twice. As long as you do that, okay, then you're going to have exactly n zeros, whatever the degree of the polynomial is. All right, so looking at this one now, we have a 3x to the fifth plus 24x cubed plus 48x. Because this is x to the fifth, that's the degree of our polynomial, we know in this case there's going to be 5 total zeros. Okay, and so we're looking for all 5 zeros of this polynomial. Now, the first thing I'm going to do on this one is I notice there's actually a common factor of x. I can't do my p's and q's here because I don't have an actual constant value. Okay, so keep in mind, the only way we can do p's and q's and do our rational zero theorem is if we actually had a constant term down here at the end, and we don't this time. So I'm going to go ahead and try factoring this. I see a common factor of x, and I see a common factor of 3 here. I'm going to factor out a 3x. That's going to leave us now with x to the 4th power plus, this is going to give us an 8x squared plus, and then down here we're just left with a 16. All right, now looking at what's left over in my parentheses, that trinomial, I notice that I've got 3 nice terms that have an x to the 4th, and x squared is the middle term, and then a constant at the end. I'm going to see if I can factor that again. So we're going to have our 3x out front. I'm going to try to break this into 2 binomials now. So x to the 4th, I'm going to use x squared and x squared. Now I need factors of 16 that will give us 8x squared in the middle. Well, 4 would work in that case because 4 times 4 is 16, and then 4x squared plus 4x squared would give us 8x squared in the middle. Okay, so I'm going to use those 2 factors there. Now, if you want to, right, we could rewrite that then as 3x times x squared plus 4 all squared, since we have that x squared plus 4 factor twice. Now I can actually set each one of my factors equal to 0 to find the actual zeros of this polynomial. Well, 3x is one of our factors, so I'm going to say 3x equals 0. My other factor is x squared plus 4. And I only need to use it once, right? Because solving it twice would just give me the same values multiple times. Now for this first one, I'm just going to divide by 3. 0 divided by 3 gives us 0. So x equals 0 is one of our zeros. Now with this other one, when I set it equal to 0, I'm going to subtract the 4. That gives us x squared equals negative 4. Then we take our square roots. That gives us plus or minus the square root of negative 4. And now the square root of negative 4, remember, is going to give us a 2i. We have plus or minus 2i. Now, when we list out our zeros here, we know that 0 is one of the zeros. We know that positive 2i is a 0. And we know that negative 2i is a 0. Well, that's only 3. We said we should have 5 because the degree of this polynomial is 5. But remember, we had this square on that factor right there, which means that every 0 that comes out of that factor is going to have a multiplicity of 2, meaning we have to count it twice. So the 2i and the negative 2i actually happen 2 times. And so now when we actually count up our zeros, we actually have 5 total zeros because the 2i and the negative 2i happen twice in that polynomial. And if you're doing these problems in WebAssign, also keep that in mind. They're going to ask for you to list out zeros and include repetitions. So you actually do have to list out the 2i and the negative 2i twice for a problem like this. All right, so now we want to work backwards. We're given the zeros of this polynomial. We're asked to find a polynomial of degree 4 that has those zeros. Well, remember, if we know the zeros, then we also know the factors. So in this case, I'm going to start with that. So I've got x minus I has to be a factor since I is a 0. X plus I must also be a 0 or factor because negative I is a 0. X minus 2 is a factor because of the positive 2, and x plus 2 is a factor because of the negative 2. So whenever you're given the zeros and asked to find a polynomial, start with the factors that come from those zeros. Now we're going to go ahead and multiply this stuff out. We'll come back to the fact that P of 3 equals 25. We'll do that at the end. Okay, so we're just going to FOIL all this out, distribute everything, combine like terms. I'm going to start with my first 2 sets of parentheses here. X times x should give us x squared. Then we're going to have a plus xi and a minus xi. Those terms are going to cancel. And then we have a negative I squared. Okay, then we'll do these other 2. X times x is x squared. Positive 2x and negative 2x, those middle terms cancel out. And negative 2 times 2 should give us a negative 4. Now remember, I squared is equal to negative 1. And that's something we discussed back in section 1.6. So now when I do this, this is going to give us x squared plus 1 times x squared minus 4. We're subtracting a negative 1 there, and that subtraction of a negative 1 becomes an addition. Now we can FOIL what we've got left here. When I do that, I'm going to have x to the 4th power. We're going to have a minus 4x squared and a plus 1x squared. That would be negative 3x squared. And then a 1 times negative 4 should give us a negative 4. Now, the only thing left is to figure out what the polynomial would be if P of 3 is equal to 25. Because keep in mind here, we can actually multiply this by some a value out front. That's not going to change the zeros, and so we might get different coefficients here. So the way I'm going to solve this is I'm going to say a times, I'm going to plug in 3 for my x's. So 3 to the 4th minus 3 times 3 squared minus 4. And I need all of that to equal 25 this time. All right, so now if we work out everything that's in the parentheses there, that should give us 50. We're going to have 50a is equal to 25. Then we can divide by 50, and that's going to give us a equals 1 over 2. Right? 25 over 50 is just 1/2. That means that my a value that I'm multiplying this polynomial by is just going to be 1/2. So I'll come back and say, well, this is 1/2 times x to the fourth minus 3x squared minus 4. And distributing that gives us 1/2 x to the fourth minus 3/2 x squared minus 2. And so that would now be the polynomial that would have those zeros of I, negative I2, and negative 2, and would also have a P of 3 value of 25. All right, now the second one here, we're looking for Q of x, needs a degree of 4. Zeros are negative 2 and 0, where negative 2 is a 0 of multiplicity 3. So what that means is that when we list out our factors here, we know negative 2 is a 0, which means that x plus 2 has to be a factor. But because that has a multiplicity of 3, I know that factor is going to happen 3 times. We're going to have x plus 2 and x plus 2 again. And then our other 0 is just 0, so that's just going to be a factor of x. Now again, we're just going to multiply this out. I'm going to start here with my first 2. It's going to give us x squared plus 2x is plus 4x. 2 times 2 is 4. Now I'm going to go ahead and distribute this x here. So we're going to get x squared plus 2x. Now we can multiply. Now, again, if you want to use the box to help you understand exactly what you're multiplying together, feel free to do that. If you don't need it and you can just distribute, that's fine also. I'm going to set up my box over here. I'm going to list out my x squared, positive 4x, positive 4. Across the side here, we have x squared, and we have 2x. Now we multiply. That's going to give us x to the fourth, 4x cubed, 4x squared, 2x cubed, 4x squared, and 8x. Combine like terms now. We have x cubed terms here, x squared terms here. So we're left with x to the fourth plus 6x cubed plus 8x squared and plus 8x. Now this time we didn't have any additional criteria like the P of 3 equals 25 from the other problem. So this right here is our Q of x polynomial now. So again, just keep in mind, if they're giving you a multiplicity of something, that means that you need to count that factor that many times. So just make sure you actually list it out that many times. Now we actually multiply everything out. And remember, we should have had a degree of 4 in the end, right? So if you don't get a degree of 4, then you know you did something wrong. In this case, we have an x to the fourth power as the degree of that polynomial. All right, now we're going to find all 4 zeros of this polynomial here. All right, so same steps. We're going to start with our p's and q's because this time we do have a constant term at the end. So our p values here, plus or minus 1, plus or minus 2, plus or minus 4. Q values, leading coefficient, plus or minus 1, and plus or minus 3 this time. Now we do our p's over q's. That's going to give us plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. So again, lots of options this time. So I would go to my graph. In this case, it looks like 2 might be a 0. I'm going to use 2 here. Again, list out your coefficients. We have 3, negative 2, negative 1, negative 12, and negative 4. No missing terms this time. Bring down your 3. 3 times 2 is 6. Negative 2 plus 6 is 4. 4 times 2 is 8. Negative 1 plus 8 is 7. 7 times 2 should give us 14. Negative 12 plus 14 is 2. 2 times 2 is 4. And that does give us a remainder of 0. Okay, so now we know that one of our zeros is positive 2. Now, again, looking at my graph, another place that it looks like it might cross is somewhere between 0 and 1. Okay, so in this case, we've got 1/3 and 2/3 as the two options there. I'm going to go with the 1/3 here because it looks like it's closer to 0 this time. So I'm going to test 1/3. Sorry, it's between 0 and -1, so that should actually be -1/3 instead. All right, so now we're going to bring down our 3. 3 times -1/3 should give us -1. 4 plus -1 is 3. 3 times -1/3 is -1 again. 7 plus -1 is 6. 6 times -1/3 is -2. And again, we do get a remainder of 0 here. So -1/3 is also one of our zeros. Now, at that point, we've taken out 2 of our zeros. We started with x to the 4th. So we know this line down here represents a quadratic, x squared. I'm going to go ahead and start listing out our factors. This is x minus 2, x plus 1/3, and then 3x squared plus 3x plus 6. Now, what I notice here is that I actually have a common factor of 3 in this quadratic down here at the end. I'm going to go ahead and pull that out. I'm going to have 3 times x minus 2 times x plus 1/3 times x squared plus x plus 2. And the only real reason to do that is it makes the value smaller because now I can see if that thing factors, and if it doesn't, I'm going to have to use quadratic formula, but I don't have to deal with the larger values of 3 and 6. I can just use the 1s and the 2s now. Okay, so this does not factor. I am going to have to use quadratic formula. So we're going to have x equals negative b, it's going to be -1, plus or minus the square root of 1 squared minus 4 times 1 times 2 all over 2 times 1. Now we simplify that. So that's going to give us -1 plus or minus the square root of, it's going to be 1 minus 8, so that's -7 over 2. And now we can't take the square root of 7, but we can bring the negative out as an I. That's going to give us x equals -1 plus or minus I times the square root of 7 all over 2. So in terms of our zeros now, this is going to be -1 plus I square root of 7 all over 2, and -1 minus I square root of 7 all over 2. And that's all we were asked to find there are the zeros, right? So we found our list of zeros. These would be the 4 zeros of that polynomial now. Now, if you needed to get the complete factorization, right, then you could use those zeros for that factorization. Another thing you might see sometimes with my factors over here, rather than leaving that fraction of 1/3, since I have a 3 on the outside, I can actually distribute that into just this factor right here. And that would give us x minus 2 times 3x plus 1 times x squared plus x plus 2. Right? And then that way we just don't have that fraction within a factor, right? We get the 3x plus 1, which is still going to give us the same 0, right? We would subtract 1, divide by 3. We still get -1/3 as the 0 from that factor now. Now, in terms of WebAssign, right, just so you're clear, it's going to ask for these things in a plus bi form. So with this -1 plus and minus I squared root of 7 over 2, you would actually have to write this as -1 over 2 plus square root of 7 over 2 times I, and -1 over 2 minus the square root of 7 over 2 times I. Because that way you actually have it in the a plus bi form. In this case, the a value is -1/2 for both of them, and then your b value is either positive square root of 7 over 2 or negative square root of 7 over 2. So on a test, right, what I've got boxed up there at the top, that's perfectly fine. You can leave your zeros just like that. But if you're inputting them into WebAssign, they're going to want it in A plus BI form. So you're just going to make sure that you actually enter them like this instead. All right, now conjugate zeros theorem. So if the polynomial p has real coefficients, and if the complex number z is a zero of p, then its complex conjugate z bar is also a zero of p. We kind of mentioned this back in section 1.6, right? That if you actually use quadratic formula and you get a complex number, we know its conjugate is also going to be a zero. Same thing here now, right? So in terms of zeros of a polynomial, if z is a complex zero, then its conjugate also has to be a zero of that polynomial. All right, so now we want to find a polynomial that has a degree of 3, integer coefficients, and its zeros are 1/2 and 3 minus I. Notice here they only gave us 2 zeros, right? 1/2 and 3 minus I. We need a degree of 3, which means we need 3 zeros. But based off the conjugate zero theorem, we know that if 3 minus I is a 0, then 3 plus I, its complex conjugate, also has to be a 0. So now we have all 3 zeros of that polynomial. So now we can start our factors. We're going to have x minus 1/2. That would give us a 0 of 1/2. X minus 3 minus I would give us the 3 minus I. And then x minus 3 plus I would give us the 3 plus I. Just remember, it's always x minus whatever your 0 is. That's going to be your factor. Now, before we actually FOIL all this out, right, and distribute everything, let's just distribute the negatives inside here. So we're going to have x minus 1/2, x minus 3 plus I, and x minus 3 minus I. Now, whenever I've got complex numbers, imaginary values inside my factors, I'm going to start with those factors first because a lot of times stuff is going to cancel out and it'll make the distributing to the x minus 1/2 a little easier. So I'm going to do my box again since I've got 3 terms. So we have x, negative 3 and I, x, negative 3 and negative I. All right, so now when we multiply, we're going to have x squared. We're going to have a negative 3x, positive xi. Next line here is going to be negative 3x, positive 9, negative 3i. And then our last line, negative xi, positive 3i, and negative I squared. Now remember, I squared is equal to negative 1. So this value right here is actually going to become a positive 1. So we have a negative 1 this time. Now we can combine like terms. I'll keep my x minus 1/2 factor here. We have an x squared that doesn't combine with anything, so x squared. We have negative 3x and a negative 3x. That's going to give us a negative 6x. Our xi and negative xi, those terms are going to cancel. Our 3i and negative 3i, those terms are going to cancel. And now we have this positive 9 and positive 1 that we can combine. That's going to give us a positive 10. Now we've gotten rid of all the imaginaries. Now we can just distribute these other 2, right? So again, I'm going to do my box. That's going to give us x squared, negative 6x, and positive 10. And then down the side here, we're going to just have x and negative 1/2. All right, so now we have x cubed. We have a negative 6x squared. We have a positive 10x. We have a negative 1/2 x squared. A positive 3x. And a negative 5. Combining like terms here, we have our x squared terms and our x terms that will combine. So that'll give us x cubed negative 6x squared, and then a negative 1/2 x squared. That's going to be negative 13 over 2x squared. This gives us a positive 13x, and then a minus 5. Now, the only thing left at this point is it tells us we want integer coefficients. Well, I've got a fraction, right? I've got a rational number instead of an integer as one of my coefficients, so I need to get rid of that. But remember, we're allowed to multiply a polynomial by any factor that we want that's not going to change the zeros, right? So in this case, to get rid of that fraction, I can just come out here and multiply this whole thing by 2. That'll get rid of the fraction and give me only integer coefficients, and it will not change any of my zeros. So that's going to give us 2x cubed minus 13x squared plus 26x minus 10. And so this would now be our polynomial, has a degree of 3, has the appropriate zeros, and it only has integer coefficients this time. All right, now linear and quadratic factors theorem. So every polynomial with real coefficients can be factored into a product of linear and irreducible quadratic factors with real coefficients. Okay, so basically, we've gotten everything down to a completely factored form where it's all linears, but we could have complex numbers, imaginary values in there. This is telling us now that anything that is going to give us either an irrational value or an imaginary value can at least be gotten down to a quadratic factor. So any polynomial, we can at least get down to linear and quadratics without having to deal with irrational values or imaginary values. All right, so we want to try to factor this into its linear and irreducible quadratic factors, and then we'll do the complete linear factorization for the second part here. All right, so the first thing I notice here is I've got a trinomial. It is x to the fourth. I'm going to try just factoring this as is, right? So I'm going to break this into two binomials. To get x to the fourth, I'm going to use x squared and x squared. Now I need factors of 8 that would also give us 2 in the middle, right? Well, 4 and 2 could work if my signs are correct. So I'm going to go with 4 and 2. I need a negative 8, which means my signs need to be different, positive and negative. And I need a positive 2x squared, so I'm going to go with a positive 4 and a negative 2. So that would give us a negative 2x squared, a positive 4x squared. That's 2x squared in the middle. Positive 4 times negative 2 does give us a negative 8. So that is the factors of that polynomial now. Now, notice in this case, right, the x squared plus 4, that's a sum of squares that is an irreducible quadratic factor. We also have the x squared minus 2 that is not a difference of squares because 2 is not a perfect square, so that is also an irreducible quadratic factor. Okay, so now we've got this thing down to the irreducible quadratics. Now we want to get the linear factors for the second part. So to do that, we need to know all the zeros. So I'm going to take each one of these factors now, and I'm going to set it equal to 0. So x squared plus 4 equals 0, and x squared minus 2 equals 0. Solving this now, we get x squared equals negative 4. Taking our square root gives us plus or minus the square root of negative 4. And we've done that one several times now. That's going to be plus or minus 2i. Now this other one, if we move the 2 over, we get x squared equals 2. Take your square root, you're going to get x equals plus or minus the square root of 2. We cannot simplify the square root of 2. That is just an irrational value now. So now in terms of our zeros, if we wanted to list those out, we know our zeros are going to be 2i, negative 2i, square root of 2, and negative square root of 2, right? And remember here, we had an x to the fourth power. That means we should have 4 zeros. Those are all 4 zeros of that polynomial. Now we can write the linear factors from those zeros. We're going to have x minus 2i, x plus 2i, x minus the square root of 2, and x plus the square root of 2. So again, the difference here is that first one is just irreducible quadratics because I can't get any other factors there without using irrational numbers or imaginary numbers. But if you want the linear factors, you have to find all the zeros and actually use the irrational and imaginary values now for those linear factors. All right, so that's all we've got for section 3.5. Again, always send me questions through WebAssign. If you have any questions on the homework, come see me during student hours if you need to. Have a great day, and I will see you next time.